Hello, everyone, and welcome. Today we're diving into one of the most important topics in probability, the binomial distribution. We'll be looking at Section 8b, the binomial distribution. By the end of today's class, you will be able to identify situations that can be modeled by a binomial distribution, and you'll be able to calculate probabilities as well as the mean and variance for these scenarios. Specifically, our learning objectives are to first, identify the conditions for a binomial distribution. Second, to calculate binomial probabilities for different situations. And third, to calculate the mean and variance of a binomial distribution. So what is it? The binomial distribution is a specific type of discrete probability distribution. It's incredibly useful because it models many real-world situations that have a certain structure. For a random variable to follow a binomial distribution, 4 specific conditions must be met. Let's go through them one by one. First, there must be a fixed number of trials. We'll call this number n. This means we know from the start how many times we're going to repeat the experiment. For example, we decide to flip a coin 10 times. Here, n is 10. It's a fixed number. Second, each trial must have only 2 possible outcomes. We usually label these as success and failure. Think of a multiple choice question. You either get it right, success, or wrong, failure. There's no in between. These are the only 2 possibilities for each trial. Third, the trials must be independent. This is a crucial one. The outcome of one trial cannot influence the outcome of another. If we're rolling a die, the result of the first roll has no effect on the result of the second roll. They are independent events. And fourth, the probability of success must be the same for each trial. We'll call this probability P. If we're flipping a fair coin, the probability of getting ahead is 0.5 on the first flip, the second flip, and every flip after that. The probability P remains constant. So to recap, for a situation to be binomial, we need a fixed number of independent trials, each with 2 outcomes, and a constant probability of success. If all 4 of these conditions hold, we have a binomial distribution. Now let's practice identifying these scenarios. It's not always obvious if a situation fits the binomial model. Our goal here is to learn to check if the 4 conditions are met. So our objective for this part is to check if a given scenario meets those 4 binomial conditions. Let's look at an example. Imagine a drawer with 5 black socks and 3 red socks. We pull out 2 socks, one after the other, without putting the first one back. Let's define our random variable x as the number of black socks we pull out. The question is, can x be modeled by a binomial distribution? Let's check the conditions. First, is there a fixed number of trials? Yes, we are pulling out 2 socks, so n equals 2. That condition is met. Second, are there 2 outcomes for each trial? Yes, a sock is either black or it's red. We can define success as pulling a black sock. So this condition is also met. Now for the third and fourth conditions, which are related. Are the trials independent, and is the probability of success constant? Let's think about the probability of success on the first trial. There are 5 black socks out of a total of 8. So the probability of the first sock being black is 5/8. But what about the second trial? Because we did not replace the first sock, the total number of socks has changed. The probabilities for the second draw depend on what we drew first. If the first sock was black, there are now 4 black socks left and 7 total socks. The probability of the second being black is 4/7. If the first sock was red, there are still 5 black socks, but only 7 total. The probability is 5/7. Notice the problem here. The probability of success on the second trial is not constant. It changes based on the first trial. This also means the trials are not independent. So, conditions 3 and 4 fail. Since not all conditions are met, this scenario cannot be modeled by a binomial distribution. This is a classic example of sampling without replacement. The correct model here is actually called the hypergeometric distribution, but we won't be covering that today. Now, if a random variable x does follow a binomial distribution with n trials and a success probability of p, we use a special notation. We write x, a tilde symbol, which means is distributed as, b for binomial, and then in parentheses n comma p. So x is distributed as binomial with parameters n and p. For instance, if we toss a fair coin 30 times and x is the number of heads, all 4 conditions are met. We have 30 fixed trials, 2 outcomes, heads or tails, The flips are independent, and the probability of heads is always 0.5. So we can write x is distributed as b 30.5. We have now seen how to check the four conditions and how to use the proper notation for a binomial distribution. This is a fundamental skill for the rest of our work. All right, now that we can identify a binomial distribution, let's learn how to calculate probabilities. Our objective here is to use our calculators to find probabilities for binomial scenarios. We'll be focusing on how to use our graphing display calculators, or GDCs, to find these probabilities. Let's use an example. An archer hits a bullseye with a probability of 0.3. She takes 10 shots. Let x be the number of bullseyes. First, let's confirm this is binomial. We have a fixed number of trials, n equals 10. We have two outcomes, bullseye or miss. The shots are independent, and the probability of success, p, is constant at 0.3, so x is distributed as b10.3. Now, let's ask a question. What is the probability that the archer hits exactly 3 bullseyes? We are looking for the probability that our random variable x is equal to exactly 3. For this, we use the binomial probability distribution function on our calculators, often abbreviated as binomial PD or binom PDF. This function calculates the probability for a single value. We input our variables, x equals 3, the number of trials n is 10, and the probability p is 0.3. The calculator gives us the result, which is approximately 0.267. So there's about a 26.7% chance of her hitting exactly 3 bullseyes. Now let's try a different type of question. What is the probability that she hits at least 3 bullseyes? This means we want the probability that x is 3 or 4 or 5 all the way up to 10. We're looking for px is greater than or equal to 3. Calculating each of these probabilities individually and adding them up would be tedious. Instead, we use the complement rule and another calculator function. The opposite of at least 3 is less than 3, which for a discrete variable means 0, 1, or 2. So x is less than or equal to 2. The probability of x being greater than or equal to 3 is equal to 1 minus the probability of x being less than 3. Since x must be an integer, being less than 3 is the same as being less than or equal to 2. To find the probability of x being less than or equal to 2, we use the binomial cumulative distribution function, often binomial CD or binom CDF. This function sums the probabilities from 0 up to a specified value. We input x equals 2, n equals 10, and p equals 0.3. The calculator tells us that px to 2 is approximately 0.383. Now we can finish our original calculation. The probability of hitting at least 3 bullseyes is 1 minus 0.383, which equals 0.617. So there's a 61.7% chance she hits 3 or more bullseyes. So we've learned the two main calculator functions, binomial PD for exactly equals, and binomial CD for less than or equal to, which we can combine with the complement rule to find greater than probabilities. Let's tackle a common point of confusion, handling strict inequalities with discrete distributions. Our objective is to correctly translate probability statements like more than 4 but fewer than 8 into a calculation. We'll focus on how to correctly set up calculations for compound inequalities, like the probability that x is between 2 values. Let's consider this problem. Mia tosses a fair coin 10 times. What is the probability she gets more than 4 but fewer than 8 heads? First, we define our random variable. Let x be the number of heads. This is a binomial scenario with n equals 10 and p equals 0.5. So x is distributed as b10.5. We want to find the probability that x is greater than 4 and less than 8. Mathematically, we are looking for p4x8. Now this is the critical step. Since x must be an integer, you can't get 4 or 5 heads. Greater than 4 means starting at 5, and less than 8 means stopping at 7. So the statement p4x8 is equivalent to p5x7. This is the most common place to make a mistake, so always take a moment to write out the integer values included. How do we calculate this with our cumulative function, which only does less than or equal to? We can think of it as taking all the probabilities up to 7 and then subtracting the ones we don't want, which are all the probabilities up to 4. So p of 5x7 is equal to x7 minus p x before. Notice we subtract p x04, not p x5. We want to include 5 in our final answer, so we must subtract the probabilities for 0, 1, 2, 3, and 4. Now we can use our calculator's binomial CD function twice. Using our calculator for x by 10.5, we find that px.7 is 0.9453, and px4 is 0.377. Subtracting these gives us our final answer, 0.9453 minus 0.3770 equals 0.5683. This is the correct probability. Let's quickly look at some common errors. One might calculate px7 minus px3. What would this actually be? This would be p4 to x7, which includes x equals 4. Our original question said more than 4, so this is incorrect. Another common error is to misinterpret the upper bound. For example, calculating px8 minus px4. This would be p5x8, which includes x equals 8. Our question said fewer than 8, so this is also incorrect. The key takeaway is to always convert strict inequalities into inclusive inequalities first, by carefully considering the integer values. This will ensure you use the correct bounds in your calculation. Okay, let's move on to another key feature of the binomial distribution, its mean and variance. The great thing about standard distributions like the binomial is that they have simple formulas for these measures. Our objective here is to learn and apply the formulas for the mean or expected value and the variance of a binomial random variable. For a general discrete random variable, we'd have to calculate the sum of x times p of x equal x to find the mean, which can be a lot of work. But for the binomial distribution, it's much easier. If a random variable x follows a binomial distribution with parameters n and p, then its expected value, or mean, is simply n times p. It's that straightforward. This should feel intuitive. If you flip a coin 100 times, how many heads would you expect? You'd say 50. That's just n times p, or 100 times 0.5. There's also a simple formula for the variance, which measures the spread of the distribution. The variance of x is n times p times 1 minus p. Remember that 1 minus p is just the probability of failure. So the variance is the number of trials times the probability of success times the probability of failure. Let's apply these formulas to an example. Dima is taking a multiple choice quiz with 20 questions. Each question has 5 possible answers. She guesses every answer. Let x be the number of questions she answers correctly. Is this a binomial scenario? Let's check. Fixed trials? Yes, n equal 20. 2 outcomes? Yes, correct or incorrect. Independent? Yes, guessing on one question doesn't affect another. Constant probability of success? Yes, since there are 5 choices, the probability of guessing correctly, p, is 1 over 5, or 0.2. So x is distributed as b 20.2. First, let's find the mean, or the expected number of correct answers. Using our formula, the expected value of x is n times p. That's 20 times 0.2, which equals 4. So on average, we would expect Dima to guess 4 answers correctly. Next, let's find the standard deviation of x. To do that, we first need to find the variance. The variance is n times p times 1 minus p. That's 20 times 0.2 times 0.8. This gives us a variance of 3.2. The standard deviation is simply the square root of the variance. So the standard deviation is the square root of 3.2, which is approximately 1.79. This gives us a measure of how much the number of correct answers is likely to vary from the mean of 4. So you see, these formulas provide a very quick way to understand the center and spread of a binomial distribution without needing to construct the entire probability table. We've now successfully used these formulas to find the mean and variance. In our final section today, we're going to talk about the real-world application of these models and their limitations. It's important to be a critical thinker when applying mathematical models. Our objective is to critically evaluate the assumptions of a binomial model when applied to a real-world scenario. Mathematical models are simplifications of reality. The binomial distribution is powerful, but the real world is messy, and the conditions are not always perfectly met. Let's consider an example. It's known that about 1.2% of people in a country suffer from a cold at any given time. A company has 80 employees. We want to model the number of employees with a cold. Let's define x as the number of employees with a cold. Can we use a binomial distribution here? First, what assumptions would we need to make for this to be a binomial model? We would need to assume a fixed number of trials, which is our 80 employees. We need two outcomes. Either an employee has a cold or they don't. We need to assume that the trials are independent, meaning one employee having a cold doesn't make it more likely for another to have one. And we need to assume a constant probability of success, P, of 0.012 for every single employee. Now let's think critically. Are these assumptions realistic? The fixed trials and two outcomes assumptions are fine. But what about independence? Colds are contagious. If one person in an office comes to work with a cold, they are likely to infect their colleagues. This means the events are not independent. The probability of one person getting a cold is higher if their desk mate already has one. So the independence assumption is likely violated in this real-world scenario. Does that mean the model is useless? Not necessarily. It means our model is an approximation. It might still give us a reasonably good estimate, but we must be aware of its limitations and state them. We would report our results by saying, assuming the cases are independent, the probability is. Let's proceed by assuming the conditions are met, just for the sake of practice. Let's find the probability that exactly 3 employees have a cold. We assume X is distributed as B80.012. We want to find Px equals 3. Using our calculator's binomial PD function with X equals 3, N equals 80, and P equals 0.012, we get a probability of approximately 0.056. The key lesson here is that applying these models requires judgment. You must check the conditions, think about whether they make sense in the context of the problem, and acknowledge any limitations of your model. This is what it means to use mathematics thoughtfully. To cap things off, let's look at a more complex problem that involves 2 layers of binomial probability. This will test our understanding of how to combine these concepts. Our objective is to solve a multi-step problem where the result of one binomial calculation becomes a parameter in a second binomial calculation. Here's the scenario. Eggs are sold in boxes of 6. The probability that any single egg is broken is 0.06, and this is independent for each egg. So we have boxes of 6 eggs, and the probability an individual egg is broken is 0.06. Part A. Find the probability that a randomly selected box contains at least one broken egg. This first part is a binomial problem itself. Let's define a random variable, y, as the number of broken eggs in one box. For a single box, we have 6 trials, the 6 eggs. The probability of success, an egg being broken, is 0.06. So y is distributed as b6.06. We want to find the probability of at least one broken egg, which is py to 1. As we've learned, it's easiest to calculate this using the complement. 1 minus the probability of having 0 broken eggs, p of y equals 0. We can find py equals 0 using the binomial PD function on our calculator. With x equals 0, n equals 6, and p equals 0.06, our calculator gives py equals 0 as approximately 0.690. Therefore, the probability of at least one broken egg is 1 minus 0.690, which is 0.310. Okay, hold on to that number. Now for the second layer of the problem. A customer buys 10 boxes of eggs. A box is returned if it contains at least one broken egg. Find the probability that the customer returns at least one box. Now we have a new experiment. Let x be the number of boxes the customer returns. This is another binomial scenario. What are the parameters for this new distribution? The number of trials n is 10 because the customer bought 10 boxes. The probability of success, a box being returned, is the probability we just calculated, the chance that a box has at least one broken egg, which is 0.310. So our new random variable x is distributed as b at 10, 0.310. The question asks for the probability that the customer returns at least one box. That's p of x toward a 1. And once again, the easiest way to find this is with the complement rule. 1 minus the probability of returning 0 boxes, px equals 0. We use our binomial PD function for this new distribution. With x equals 0, n equals 10, and our new p of 0.310, the calculator gives px equals 0 as approximately 0.024. So the final answer is 1 minus 0.024, which is 0.976. There's a 97.6% chance the customer returns at least one box. This example beautifully illustrates how one binomial problem can be nested inside another. By breaking the problem down into steps, defining our random variables clearly at each stage, we can solve even complex scenarios. That concludes our lesson on the binomial distribution. Great work today.